The reason vectors are so important and so useful is that there's several operations we can do with them. So first, we can add two vectors to get a third vector. Geometrically, if u is a vector like this, and v is a vector like this, then to get their sum, what we do is we draw each of them. So we draw u, but then we draw v starting where the other one ended. So now we draw v like this, and then their sum is defined to be the combined arrow that like this. So this is the vector that we define to be u plus v. And we could do this in either order. So we could draw v first and then draw u starting there. So this is often called the parallelogram rule for adding vectors. So the sum of two vectors is the diagonal of the parallelogram that they give you. And you can think of this as if u tells you how to get from point A to point B, and v tells you how to get from point B to point C, then, so these are points, then u plus v tells you how to get from A to C in one go. Algebraically, to add two vectors, we just add their components together in each slot individually. Next thing we can do is scale vectors by a number. So here a scalar just means a number, but we're calling it a scalar to emphasize its role in scaling. So if u is a vector like this, then geometrically when we scale it, we just keep the direction and change the length, or at least when we multiply by a positive number. So this would be 2u. This could be 1/2 u. But then if we multiply by a negative number, so this could be negative u would be this vector, and then negative 3u, for instance, would be this vector. So the absolute value of the scalar is changing the length, and then depending on whether it's positive or negative, we'll either keep the direction or reverse it. And algebraically, to scale a vector by a number, we just multiply each of the components individually by that number. Next thing we can do is we can add a vector to a point. So if A is a point and V is a vector, then to add V to A, what we'll do is draw V starting at A, and then the endpoint of that, this is what we call A plus V. And algebraically, to add a point to a vector, we just add the components together, again, in each slot individually. So this looks a lot like the first line, but it's actually a little bit more subtle, which I'll mention in a second. And then the counterpoint to this is that if we have 2 points, we can subtract them to get a vector. So this is A, and this is B. Then the vector going from A to B is what we call B minus A. So it's what you have to add to A in order to get B. And again, algebraically, to subtract one point from another, we just subtract the components in each slot individually. Now, the subtlety to watch out for is that points cannot be added together or scaled. Like you could write those same formulas down, but you would get sort of nonsense answers. So the thing that, main example that people sometimes notice, for instance, is 0 degrees Celsius. So here I'm talking about like freezing point of water. This is an absolute temperature. This is 32 degrees Fahrenheit. And if we try to multiply both sides by 2, we would get that 0 degrees Celsius is 64 degrees Fahrenheit, which is wrong. So point quantities cannot be added together or scaled. They can only be added with a vector or subtracted from each other to get a vector. And then vectors, we can do more stuff with them, which is why they're more useful than just points. These vector operations obey many of the same algebraic rules that their counterparts for ordinary numbers do. So first, if we add two vectors, we can do it in either order, and we'll get the same result, because it's just the diagonal of the parallelogram, no matter which sort of side of the parallelogram you go around. And this property is called the commutativity of vector addition. Next, if I want to add three vectors, well, I might pair those up, add u and v first, and then add w, or I could add v and w first, and then add it to u, and we'll get the same result no matter how we pair them up. So this is called the associative property of vector addition. Then if I add any vector to the zero vector, so that's the vector all of whose components are zero, then I just get back the vector we started with. If I add a vector to its negative, so that's -1 times u, I get the zero vector. So there's negatives for, or inverses for vector addition. If we multiply any vector by the number 0, we get the zero vector. If we multiply a vector by 1, we just get back the same vector. Then if we scale by a number b and then scale that by a number a, that's the same as scaling by a times b all in one go. And then there's two distributive laws for multiplication or for scaling. We can distribute in the vector argument, so a times u plus v is au plus av, or we can distribute in the scalar argument. So a plus b times u is au plus bu. So let me just show how to prove one of these 8, for example. So see what are all the steps involved in actually justifying this rigorously. So a times u plus v. So first, let's expand out the definition of u plus v. So if these have coordinates u1 and v1 and so on, then by definition, we just do that. So that's definition of u plus v. Then by the definition of scalar multiplication, to multiply that by a, I'd multiply all of the individual components by a. So this is the definition of scaling. Now we'll invoke the distributive property for just ordinary numbers. So now we can rewrite this as au1 plus av1, au2 plus av2, au3 plus av3. So this is distributivity for just real numbers. Now we can regroup this. This is au1, au2, au3 plus av1, av2, av3, and that is au plus av, which is what we were after. So a lot of the properties of numbers continue to hold for the corresponding operations on vectors, but once we encounter the dot product and the cross product, those are operations on vectors that will behave rather differently than multiplication for numbers. So we have to watch out. So I'll leave you with just this interactive demo you can play with to visualize some of these operations.